Hello, my name is Miles Woodcock-Girard, and today I will perform an analysis and derivation for the Stokes-Einstein relation. Concluded by Albert Einstein in 1905, this elegant equation establishes a relationship between the nature of a particle's Brownian motion and its diffusion coefficient. The derivation can be summarized by the mathematical joining of two foundational equations, Stokes's law for drag force on a spherical particle moving at constant velocity, and the formula for diffusivity, a relation involving mean square displacement with respect to time. We will begin by deriving Stokes's law for the drag force upon a sphere at constant velocity. This is essentially the result of the Navier-Stokes with a very small Reynolds number. We begin by establishing the radial and polar components of our velocity profiles. This is defined partially in terms of the Stokes streamline function, shown here with the Greek letter psi. We can perform a curl on these profiles to yield an equation for vorticity, describing the spinning motion of the sphere in question. Through clever use of vector calculus identities, we can then derive the relation shown here, stating that the curl squared of the vorticity equation is equivalent to 0. We then apply a no-slip boundary condition at the sphere's surface. In this case, the hypothetical radius of our sphere is Ra. This allows us to make an educated guess for the streamline function psi. Here, Fr denotes the coefficients for the general solution of the resultant fourth-order differential equation. Obtaining the form of our differential equation, we can then substitute a function of our radius r back in to yield the powers of r in our Fr equation. We plug our f of r back into our original guess, then solve for a, b, c, and d using the boundary conditions for r equals ra and infinity, as well as our previously derived spherical velocity components, yielding our final general streamline equation. Finally, with our streamline equation in mind, we can obtain equations for our aforementioned velocity components in terms of r and theta only. Not only this, but we can also derive an equation for pressure, which is one of the final pieces of our puzzle. We can now finally calculate the force of our sphere due to the drag by integrating both shear and normal stress over the entire surface. The pressure we found is our normal stress, while our shear stress is given by the equation on the top right. Finally, we will add these forces together. We set up our integrals using pressure and shear stress to arrive at our answers. Finally, we sum up the resulting forces, thus completing our derivation. With this new tool, we will move back onto the second and final building block of the Stokes-Einstein relation. We begin with the formula for mean square displacement of a particle's random walk over time, its position denoted by x. We can express the displacement with the following integral from 0 to t with respect to a new time that we will denote t1. Substituting this back into our mean square displacement formula, we have instantiated a second time variable, t2, and have introduced the velocity correlation function. We instantiate tau, denoting the difference in time between t1 and t2, and perform a change in boundaries and variables, yielding the following alteration. This simplifies rather nicely to the following shorter integral, with the assumption that 0 is less than t1 is less than t2 is less than t. For our penultimate step, consider the following mobility function denoted by q. We have already established the equivalence between the integral and our diffusivity term. As well, substituting the inverse of our previously calculated Stokes monomial, the inverse taking the place of q at low Reynolds numbers, this equation is beginning to look very familiar. Indeed, when we arrange the equation for d, we arrive at last at the famous Einstein-Stokes relation. I hope you enjoyed this presentation.